All right, this is section 2.2, video 2. So we're going to finish this one up. So we're going to define what we talked about very briefly in the previous video, something which is called a point of inflection, or easier to say, inflection point. Relatively, I mean, all it is that it's a place where the graph changes concavity. It's got to change from concave up to concave down, or from concave down to concave up. And how we find that mathematically or algebraically is it's where the second derivative is going to equal 0, or where the second derivative doesn't exist. So as you can see, we've got some sketches here for you. The first one, it shows the graph going from concave down to concave up. Right there at that point, it changes. You can see how it's concave down, frowny face, to concave up, smiley face. In the second one, the second derivative here doesn't exist, but the concavity still changes. The second derivative doesn't exist because it would be undefined here, be a vertical, sec, uh, be a vertical asymptote or something. I'm actually not giving you the right word there. And it'd be a vertical tangent, excuse me. That's what I was looking for, geez. But anyway, you can see how it changes from concave down to concave up right there at that point. Um, and in the third one, it just changes from concave up to concave down. And in the fourth one, it's not actually a point of inflection. So what you can see here is that the second derivative would not exist because that would be at a cusp. But it goes from concave down to concave down. So the biggest thing is when you're checking for an inflection point, concavity must change around that inflection, around that point to be an inflection point. Otherwise, it's just some kind of a critical value of the second derivative. All right, let's go ahead and take a look at an example where we're actually going to find inflection points. So we've got our example, f of x equals 3x to the fifth minus 20x cubed. To figure out if something is an inflection point, we need the second derivative. In order to get to the second derivative, we need the first derivative, which is going to be 15x to the fourth minus 60x squared. I don't even really need to worry about doing anything with this because all I'm trying to do is find inflection points. So let's go ahead and take the second derivative. And we have actually already done this one if you hadn't already noticed. It's going to be 60x cubed minus 120x. Okay, in order for us to find inflection points, we need to figure out whether concavity changes when the second derivative is 0 or undefined. Since it's polynomial, it cannot be undefined. So let's set it equal to 0, and we're going to solve this one. So basically, we're finding critical values of the second derivative. Let's go ahead and factor out. It looks like we can factor out a 60x, which is going to leave x squared minus 2, it looks like. So either x is 0, or in the second one, you got to be careful here, x is going to be either the plus or minus square root of 2. Not a nice number to deal with, but we'll still work with it. All right, so here I'm going to go ahead and kind of go back to what we used to do with the first derivative test. I'm just going to create myself a little number line here and put all the possible inflection points on there. So I've got negative square root of 2, 0, and positive square root of 2, making sure I'm going numerically left to right. So now we're testing the second derivative for concavity. So let's go ahead and check the second derivative by plugging specific points which are around the points that we were given here. So something which is less than the negative square root of 2. Well, square root of 2 is approximately 1.4. So something less than that is going to be like negative 2. If I plug a negative 2 into these things right here, plugging a negative 2 into the 60x is going to give me a negative value. Plugging a negative 2 into the inside there, negative 2 squared is 4 minus 2 is positive. So I'm going to get a negative times a positive, which is negative, which means that this is concave down. So here I'm going to draw my little frowny face. Okay, something in between negative square root of 2 and 0, like negative 1. So I'm going to test this section in between the negative square root of 2 and 0 by plugging negative 1 in. Again, if I plug negative 1 into 60 times negative 1, that's negative. If I plug -1 inside the parentheses, I'm going to get 1 minus 2, which is also negative. So we're going to get a negative times a negative, which is positive, which means concave up. So concavity did change at -√2. That means there's going to be an inflection point there. Okay, let's test the other intervals. If I plug in +1, well, +1 on the outside is positive, +1 on the inside is negative. A positive times a negative is negative. So we get a frowny face or concave down there. And then the last one, if I plug in something bigger than √2, like 2, into both the 60x and the x² minus 2, I get positive times positive, so it is going to be concave up. So the concavity changed at all of my second derivative zeros, which means that I have inflection points at all of them. Now, in order to actually find an inflection point, you actually have to find the point. So we have to plug all of those values back into the original to find the actual point value. So I have to do f of -√2, f of 0, and f of +√2. So let's see, if I plug in -√2 into my original function, these are going to be some nasty numbers. -√2 to the 5th power is really going to be 2 times 2, which is 4, times another -√2. So that's going to be -4 √2 times 3, which is -12 √2. And then if I plug -√2 into x cubed, that's going to be 2 times the -√2. So that's going to be plus 40 √2, which is going to end up giving us 40 √2 minus 12 √2 is 28 √2. 28 √2. So my first inflection point is going to be the point -√2, 28 √2. That is the first inflection point. Inflection point. Okay, I got to plug in 0. This is the easiest one. If I plug 0 into the original function, I get 0. So I also have an inflection point at 0, 0. And then I'm going to have an inflection point at √2, comma, whatever we get there. So let's see, √2 to the 5th power is 2 times 2, which is 4, times the √2. So we're going to get 12 √2. I'm betting it's going to be just the opposite of the first one. And then, yes, it's going to be minus 40 √2. So this one's going to be -28 √2. -28 √2. Okay, not the easiest numbers to deal with there, but those are your excuse me, those are your inflection points. Those are the points where the concavity of the graph will change. All right. So we can use derivatives to gather a lot of information about functions, and we can use that information to interpret the graphs of functions. We won't do a lot of the curve sketching that I did in the previous page and that we're going to finish this thing off with here, because the calculator can do this and it can do it with very good detail. Some things calculators can't show us really well, but for the most part they do good. So we'll just do a few examples. The process of sketching curves, however, it gives you a really good, deep, and detailed understanding of how a function works and what all the components of the derivatives actually give us. So remember, strategies for sketching the graphs. You want to find the derivatives and the domain, find f prime, find f double prime, and note the domain of f. You want to find all the critical values which come from f prime either equaling 0 or does not exist. That'll give you where it's increasing and decreasing. You can get the relative extrema, maxes and mins. And you can use the first derivative test to find that. Then you're going to get your inflection points by doing the second derivative, seeing where the second derivative equals 0 or does not exist, and then checking the intervals of concavity to see whether you actually have inflection points. And then we can sketch the graph by putting A to D all together. Note that your textbook might actually give this to you in a slightly different method. So whichever method you prefer to use is the one that you should do. All right, one last example here. Find any relative extrema and graph the function of f that's given by x cubed minus 3x plus 2. Fill in the blanks below with the information that you gather about the function. It just might be helpful. We'll fill them in as we go. Okay, so one thing we know that this is a polynomial function. Therefore, the domain is all real numbers. We don't have to worry about there being any kind of undefined derivatives. So let's go ahead and start by taking the first derivative. First derivative here is going to be 3x squared minus 3. Okay, I know I'm going to need, from the first derivative, I'm going to need to set that equal to 0 to find my critical values. So we can factor out a 3 or divide a 3 out. So we get x squared minus 1 equals 0. So x is going to equal plus or minus 1. That doesn't look very good. X is going to equal plus or minus 1. There we go. So we've got our critical values at positive and negative 1. Let's figure out where it's increasing and where it's decreasing. All right, if I plug in negative 2, plugging in negative 2 to x squared minus 1 is going to give me a positive value, increasing there. Plugging in a number in between negative 1 and 1, like 0, into x squared minus 1 gives us a negative value, decreasing there. Plugging a number greater than 1 into my x squared minus 1, like 2, is going to give us a positive value, so increasing there. And what that shows us is that we have a relative max at the point negative 1. I don't know why it keeps, whoops, sorry about that. Okay, let's get rid of this somehow. There we go. Jeepers. Okay, we're going to have a relative max at negative 1. Now we have to plug negative 1 back into the original function. This one won't be so hard. Negative 1 cubed is negative 1 minus 3 times negative 1, so that's plus 3. So negative 1 plus 3 is 2, plus 2 more is 4. That's where my relative max is. The relative max is 4 at x equals negative 1. We're going to have a relative minimum at positive 1. And then plugging 1 in, we get 1 minus 3, which is negative 2, plus 2 is 0. All right. Now we're going to need the second derivative. Second derivative here is pretty easy. That's just 6x. We're going to set that equal to 0. So x equals 0. It is basically the critical value of the second derivative. That tells us where we have a potential for an inflection point. Let's test the concavity around that. So if I plug a number in less than 0, like negative 1, we get a negative, which means it's concave down. Plugging a number greater than 0, we get positive, which means it's concave up. So we do have an inflection point. Inflection IP at 0, and then we have to plug 0 back into the original to find the actual y value. Plugging 0 back into the original function just gives us 2. So we have an inflection point at 0, 2, which means that's where the concavity will change. All right, so let's put all this together. I'll have to scroll back and forth. Let's see, so increasing. We are increasing, it looks like, from negative infinity to negative 1, and then again from 1 to infinity if we look right here at this sign chart. So negative infinity to negative 1. Negative infinity to negative 1. And then again from 1 to infinity. And then it was decreasing in between those values. You can look at your own paper and you don't have to scroll. But I'm pretty sure it was decreasing from negative 1 to positive 1. Okay, the maximum value was at negative 1, 4. Negative 1, comma 4. The maximum itself was 4. The minimum is at 1, 0. So the minimum value is actually 0. Concave up. This was concave up from 0 to infinity. That's where we had the smiley face. and it was concave down from negative infinity to 0. So my point of inflection was actually at the point 0, 2, if I'm not mistaken. Let's double check that. Yes, it was 0, 2. All right, so now I've got all the information that I need right next to my graph. It should make doing the graph a little bit easier. Okay, so let's go ahead and plot whatever points we have. We know that we have a maximum at the point negative 1, 4. We have a minimum at the point 1, 0. We have a point of inflection at the point 0, 2. That's where the concavity is going to change. Okay, I know that the function is increasing from negative infinity to negative 1, and then it's decreasing from negative 1 to 1. But it's also going to be concave down from negative infinity to 0. Well, that makes sense. So it's going to be a function which looks something like this. So you can see that that is increasing right here up until I get to the point negative 1. And then it's decreasing, but it's still concave down all the way up until we get to 0. It's still got to be decreasing now, but now it's got to change to concave up, which it does. So now it's going to go concave up. It's going to hit its minimum at 1, and then it's going to continue to increase and be concave up forever. So there's a good sketch of your graph. Again, the only other thing I probably should have done was figured out what the x-intercept of the original graph was, but that's something that we didn't have to do here. Okay, that is all for video 2, a little bit shorter than video 1. You should have plenty enough now to finish the section.